Yeah, don't worry if it's backed up, not backed up, anything like that. Okay. All right. The reason that I was passing out the iPads is we've got some homework due tonight and next time, right? So I want to give you a chance today to work on this and hopefully finish it. Okay. So I'm going to talk at you for a little while. All right. And then we're going to work together on our homeworks, okay? Using the iPads or your laptop or your phone. If you want to use your phone, is great. Well, that's not great, but it's usable, okay? So we're going to do that in the last part of the period. So I'm going to talk at you for a little bit, and then we'll stop, and then we'll do that, okay? So we can all be either finished or almost finished, right, before these due dates, right? One of which is tonight, right? Remember the 1.2 homework is due this evening, okay, at midnight, right? And then we've got this quiz coming up next time, so we'd like to get that out of the way as well, okay? So that's what we're going to do today. And Taylor will be here in a few minutes, so Taylor will also be here. And so when you're doing your problems, you can ask us questions. Of course, you can also, as usual, ask your partners questions to help you understand the homework problems. Do y'all have any particular questions that you want to ask at the moment? I think the last two people who had not given me the little activity sheet from last time gave it to me, so I've got those, right? Okay, if you were here last time, and so I'll hand those back to you next time. Now, I know that some of you, or maybe a few of you in the class, still have not purchased access to my math lab. So if you're in that boat, I have printed copies of the, so you won't be able to work on the homework right online. I have printed copies of those assignments. So if you need a printed copy of either the 1.2 homework or the quiz, you can have a printed copy so you can work on that. And then when you get access, that will make the homework easier for you to work on when you get access. But if you are having difficulty with getting access, right, for whatever reason, you can follow these instructions. So you can go see Dr. Caesar in the Gator Success Center, which is in North 310. That's on the main floor, right? In the one main building, there with, where not where admissions is, but that long hallway, right, in the one main building. You can, close to advising, close to where academic advising is. And you can inquire in there. She may be able to assist you with this, okay? So it's getting kind of to the time where we need to have access. So if you don't have access, I strongly encourage you to go see Dr. Caesar there in the Gator Success Center, okay? But I have these printed copies. So when we start working on the homework, you can work on a printed copy of the homework assignment. All right. Okay, so I think that's sort of all of the logistical things I wanted to say. So again, I'm going to talk at you here for a little while, all right, and then we'll stop, and then we'll get our chance to work on our homework. Okay. We will do the roll. Yeah, Taylor will help. Taylor will start that in a second. Taylor, you want to start the roll in a few minutes here? I'll tell you about the rest of this stuff later. So, okay. All right, so I'm going to start talking now. So listen to me for a while, and then before we do other things. So remember, last time we were trying to set up the machinery that we need from algebra to help us with understanding and analyzing our data tables. And so we were going backwards to some very foundational ideas from algebra, and then we're going to develop these ideas a little bit further, but they're going to start out very basic at first, very elementary at first, and then we're going to develop them somewhat so that they can help us with that task, right, again, of analyzing our data, okay? So we gave these definitions at the end of class last time very quickly, and we're going to review them today because we'll be spending some time with these definitions. But we gave the definition of a relation last time. A relation is just a set. It's a set of ordered pairs, right? Okay? And since it's a set of ordered pairs, every ordered pair in the relation is going to have an x-coordinate and a y-coordinate. We changed terminology a little bit here, though, although we use x-coordinate as well. But sometimes we call the x-coordinate of an ordered pair the input coordinate, or just the input, and the y-coordinate of the ordered pair, we call it the output coordinate, or just the output. So you'll hear me use all those terms, and they all mean the same thing. Sometimes I'll say x-coordinate, sometimes I'll say input, sometimes I'll say y-coordinate, or second coordinate, or sometimes I'll say output, all right? All those things mean the same thing. So a very simple definition there, a set of ordered pairs is a relation. But now, as you're going to see in some of the examples today, relations present themselves to us, though, in many different forms, okay? So at their most basic form, they're just a set of ordered pairs. But usually the way we encounter relations in practice is you don't just see a list of ordered pairs written down, okay? The relation is presented to us in a little bit more complicated and subtle fashion than this definition would suggest, okay? And we'll talk about there's really three key ways that relations will be represented in this class, okay? Now, a couple of sort of subsidiary definitions, accompanying definitions for relations. If you have a relation, then the domain of the relation is just the set of all the x-coordinates or the input coordinates out of the relation. So if you look at all the ordered pairs in the relation, you just take out the input coordinates, the x-coordinates, form a set out of that. That's called the domain of the relation. And then likewise, if you pull off the y-coordinates out of all the ordered pairs and write down that list of numbers, that's called the range of the relation. So remember, domain is associated with the x-coordinates, and range is associated with always with the y-coordinates, or the output coordinates. Okay? All right, so just those three basic definitions, but we're going to explore kind of just some elaborations on those definitions, right? Last time we saw this simple example, or these two simple examples of relations. We had a relation here that I called A, again, just this set of ordered pairs, right? And then here's a second relation called B, again, just a set of ordered pairs. Those are about the easiest examples of relations I could write down, because those relations just have very few ordered pairs in them, right? Okay. This relation only has 4 elements, 4 ordered pairs in it, and this relation only has, what, 5, right, in that relation? So those are very simple relations. But now usually the relations that we'll be considering in the class, they're going to have infinitely many ordered pairs in the relation, okay, not just a finite number, all right? But these are just simple examples to sort of demonstrate the idea of relation. Here we wrote down the domain of A, right? Remember we wrote that down last time, so we just pulled off the x-coordinates, right, out of the relation A. Here's the range of B. We just pulled out the y-coordinates out of all those ordered pairs from B. Okay, so at heart, right, these are very simple ideas. Okay. All right. Now, I want to demonstrate here that there's kind of a subtle difference between the relation A and the relation B, okay? Not just the number of ordered pairs, all right, but something a little bit more fundamental distinguishes these two relations from one another, okay? All right, so this is an easy fill-in-the-blank question, okay? Suppose I gave you this on the test, right? And I said, referring to relation B, right, fill in those blanks, okay? That would be easy to do, correct, okay? Because what does this have to be, obviously? What does this second coordinate, or this output coordinate, have to be here that matches the input coordinate to what? 5, right, yeah, for relation B, that has to be 5, right, okay? So you could, everyone could easily get that answer right. Or fill in this blank, let's see. What is it, 7? Yeah, okay, because the output that matches the input 0, right, obviously there, that is 7. Let me show you now a little bit of, let me demonstrate here a little bit of mathematical notation that we use to indicate an output that matches a particular input in a relation, okay? So let me repeat that. This notation is going to indicate the output, the y-coordinate, that matches a particular input, x-coordinate, in a relation, okay? And this looks at first like it's kind of unnecessary notation. It looks like just something we've made up, to bother students, right? But actually turns out to be really useful notation, okay? What you won't like about it, though, is it kind of looks like multiplication notation. But you have to understand from the context that it doesn't indicate multiplication. All right, so here's the name of the relation B, right? That's the name that I gave this relation. And inside the parentheses there, I'm going to put the number 2, okay? Because that 2 is inside the parentheses, we are to understand that that is an input for the relation B. That's an x-coordinate for the relation B, all right? Inside the parentheses means input. And when you read this off the page, that looks like b times 2, right? Okay, but that's not the way we read this off of the page. In this context, in this relation context, we read this off as b of 2. So you don't say b times 2, but you would read that as b of 2. And it has nothing to do with multiplication, okay? No multiplication is going on here. What that means is, what b of 2 means is the output that matches the input 2. And y'all told me, what was the output that matches the input 2? What's the output that matches the input 2? 5, right, okay. So y'all told me that was 5. So b of 2 is equal to 5, all right, because 5 is the output that matches the input 2. So here we say, oh, this is equal to 5. Or if I write b of 0, right, b of 0, that's the way you read this, okay, then that's how much? 7, right, okay, because you already told me that 7 is the output that matches the input 0, okay? Let me write that in words. 7 is the output, or the y-coordinate, that matches the input 0. And then likewise, right, 5 is the output that matches the input 2 in the relation B. All right, now let me show you here what's different about the relation A, okay? All right, so suppose we had this fill in the blank, okay? Now you understand a little bit better how you're supposed to fill in that blank, right? Okay? A of minus 2 means what? That means the output that matches the input minus 2, okay? Except in this case, you're going to have a little bit of a problem filling in the blank. Let's go back with, let's go back and look at the relation A, okay? So if you look at the relation A, and we're looking for the output that matches the input 2, minus 2, what problem happens in that case? Yeah, that's right. You have some ambiguity there, right? Okay, you have a conflict. because it could be that 3 is the answer, right? 3 is the output that matches the input minus 2, or it could be 4 is the output that matches the input minus 2, all right? So you see in the relation A, there's 2 possibilities for A of minus 2, okay? Because there's 2 different outputs that match the input minus 2, all right? That does not occur, though, in relation B, okay? In relation B, if I give you a specific output, right, if I give you a specific input here, one of these inputs, there's going to be one and only one output that matches that input, okay? For that reason, then, B is a type of relation, a special type of relation that we call a function. So B is an example of a function. And what makes a relation a function is that, again, for each input, there's only one output that matches that input. For each x-coordinate, there's only one y-coordinate that matches that x-coordinate in the relation. Now that looks like, again, like a very subtle distinction there between those two types of relations, but it turns out to be really crucial and really fundamental to us. So for the most part in this course, we're going to restrict our attention to relations that are functions. We're going to be interested in only studying, for the most part, there'll be some exceptions, but for the most part, we're only going to be interested in studying relations that are functions, where each input matches only one output, where we don't have this ambiguous situation like we had in relation A, okay? So a function is a relation, but it's just a special type of relation, okay? Let me give you the formal definition of function. So here's the mathematical definition of function, and but in a minute here I'm going to give you kind of a second definition of function, which is a little bit less formal, maybe a little bit more practical. But here's the formal. If you ask a mathematician what is a function, this is what a mathematician would tell you, okay? It's just a relation where each input is matched with just one output, just exactly one output, okay? So you don't have different outputs matching the same input in a function. Now, we're getting ready to see that there are going to be several ways that we're going to be expressing or representing functions other than just listing out a long list of ordered pairs, okay? So, you know, a function is a relation is a set of ordered pairs, but we're going to have lots of, well, not lots, but multiple different ways of expressing functions other than just writing down a list of ordered pairs, okay? And the reason we're going to do that is because for most of our functions, the list of ordered pairs will be infinitely long, so we cannot write them all down. So we're going to have other more efficient ways of representing or expressing functions, okay? But again, for the most part, when we're dealing with the relations in this course, we will be concentrating or most interested on in relations that are functions. So that previous answer that I described there, what was A of minus 2, that's kind of a bogus question, all right? Okay, that's kind of a bogus question because there are multiple possible right answers to that, okay? So in a way, that is not a fair question. And that's one of the reasons why we want to focus our attention on functions rather than just relations in general. All right. Well, let's test our knowledge here of what I just said, okay? All right, so here I have a bunch of data tables, okay? You know, kind of simplified data tables. They're very short, but we can think of these as being tables of data, right? And tables of data are examples of relations, okay? A table of data, like we have been working with from the beginning of the course, those are examples of relations because you can think of, right, the matching data values in the relation, right, you can think of those matching data values as being an ordered pair, okay, right, with an input coordinate and an output coordinate. So tables of data are examples of relations. And one way that we like to express or represent relations is by using tables of data pairs, okay? So that's one of our favorite ways of writing down relations. Now, some of these relations are functions and some of them are not, so I'd like to pick out which of these four relations there constitute a function and which of them don't, okay? So what about that first one? Now, I've tried to make these a little bit deceptive to kind of fool you, but what about that first one? Is that relation an example of a function? So how do you test that, Ben? Ben says yes, okay? So, Ben, why did you say yes? It's always the same. By the way, the answer to this question is always the same, okay? It's going to be a function if each input matches just one output, okay? So is that the case here? Does each x coordinate match only one y coordinate? Yeah, you just have to just check it, right? 0, right? That x coordinate has only one matching y value, right? 1 has only one matching y value. That x coordinate 2 has only one matching y value, right? That input 3, same as x coordinate, also has only one matching output, right? Okay, and likewise for 4. Yeah, so you're right. A is an example of a function. I tried to fool you there by making the outputs the same as the inputs, okay? That has nothing to do with whether it's a function or not, all right? Okay, it's just that simple definition that I gave earlier, okay? So there you have it. That is an example of a function. And the explanation, as I mentioned, will always be the same if you have a function, right? It's because each input matches just one output, because that's what makes a relation a function. What about this one? B. So yes or no, is that a function or not a function? We're going to have to take a vote here. It's either no or yes. You're right, Montel, right? It's one or the other, okay? Yeah, there's no, this is called the, just for, to give you a name for what you just said. When something is either no or yes, right, that's called the law of the excluded middle. There's no maybe. There's no maybe with functions. It's either a function or it isn't, okay? Yeah. Uni. Yeah, that's kind of the idea, right, okay? It won't be a function if it repeats the x, okay? It won't be a function if it repeats the x. So the x here is not repeated, right, okay? Those are all distinct x values. So don't worry about the output being repeated because that's not important in a function, right? See, if I ask you, what's the output that matches the input 0, you only have one answer to give me. Or if I ask you, what's the output that matches the input 3, you only have one answer you can give me, right? It's 4 and that's it, right? Okay? So, yes, that is an example of a function, even though the outputs are all the same, okay? See, a function doesn't really rely on outputs, okay? It has to do a lot with the inputs there. Okay, Montel, now, what about C, all right? So using what Uni just said, right? Okay. She said you cannot do what in a function? Well, let's think back to the definition. The definition is each input, each x, has just one matching output. So is that the case in C?
No, sir.
Why?
Because none of them match from top to bottom.
What? I didn't understand what you just said, right? Okay.
There are no matching pairs.
There are no matching pairs. No, there are lots of matching pairs, right? Every one of these columns is a matching pair, right? Okay. But is there an x coordinate that has more than one matching y coordinate? Is there an input that has more than one matching output? Just look across there. Let's just test it one at a time. This one's small enough that we can test one at a time, Montel. So 0, how many matching outputs does it have? 1. Right. What about 1? How many matching outputs does it have? How many? Not what is the matching output, but how many does it have? For 1, well, the output is 2, but how many matching outputs do you have listed here? I only see 1, right, okay? The number 2 is that single matching output, right, okay? What about for the input 2? How many matching outputs does it have? No, I don't think so. What? It has 2 matching outputs, right, okay? Because 2 is matched with 3, and it's also matched with 4. That's what we don't want to violate in a function. Does that make sense? Okay? Yeah. So what did you say, Uni? You saw this easily because you were looking across to make sure what that doesn't happen?
The x, make sure it doesn't repeat.
Make sure the x does not repeat, right, okay? Because if the x repeats, all right, then that means probably you're going to have different matching outputs, right, okay? Ah, yes, okay. That's what Uni said. Does that make sense now, Montel? It's really important to understand the definition, all right, okay? So don't agree with me just to shut me up, okay? I really want you to understand it, all right, okay? And 4 only has that one single matching output, right, okay? But it's too late because 2 has 2 different matching outputs, cannot be a function, okay? Y'all's phones will get you in trouble, all right? Everyone has their phone out. I'm gonna have to insist that you put those away, all right, if you're gonna do that with me, all right? So, really, guys, it's college now, right? Okay? I don't think you did that in high school either. All right. What about the last one now? So Uni here, I've tried to fool you, okay, but you're not going to let me fool you, right? Okay? Is the last one an example of a function? No. Okay. Well, let's see. All right. So you're focusing on what?
The x.
The x, and what about the x?
It repeats the 3.
It repeats the 3. But, see, I got clever here, right? Because what's the matching output in both cases?
Oh, 0.
It's 0, right, okay? So I drew that one specifically to be cruel, right, okay? That one does have the same input repeated, but it doesn't change the matching output, okay? Usually you won't see that, all right? So it is a function, right, okay? Because I got that one deliberately to be deceptive, all right?
So is it only not a, wait, so it's not a function because...
It is a function. Right. Because you thought it was not a... Let's work backwards there, Chris.
I thought it wasn't because
the 3, right, okay. But notice the output is the same in both cases, right?
As long
okay.
as the output's the same.
That's right, because you cannot have the same output with different... I'm sorry, you cannot have the same input with different matching outputs, right, okay? So here, I had the same input, but the outputs were also the same, right?
Number 4.
Can you repeat that again?
You cannot have the same input with different matching outputs, okay? Not the same input with different matching outputs. So here, I tried to be clever. I gave you the same input twice, right? So you're thinking, okay, not a function, but I also used the same output in both cases. So it turns out it is a function, all right? So sometimes you do have to look a little bit more deeply than just reading the inputs and making sure that they're not repeated, okay? All right, so this one is a function, right? In spite that 3, 0 appearing twice there, okay? That counts as a function. So, look, there is one of our favorite ways now. There's one of our favorite ways now of expressing functions, and that is via tables of data pairs, okay? And in fact, we've already been using tables of data pairs, right? So we're familiar with the fact that those things show up a lot, right? Okay? Tables of data pairs appear frequently, right? Okay? But, again, as promised there are other ways of expressing functions, all right? Here is another one of our favorite ways of expressing a function, through a graph, okay? So a graph, I claim, is also a function, right? Or could be a function. A graph is also a relation, all right? Now, why is a graph, which seems like a geometric object, right, okay? Why can we think of a graph as being a relation, a set of ordered pairs, okay? So why is there this connection between graphs and this verbal description, set of ordered pairs, right? Okay, so why can we think of a set of points, right, as a relation? Okay, what's the connection between the two? Someone care to tell me there? So don't worry about if it's a function or not. Just why is a graph of set of points? Why should that be a relation? Okay, why should that sort of thing match our definition?
Can you just, I'm sorry, I don't remember. Can you define relation?
Yeah, it's a set of ordered pairs. Okay, and a graph is a set of points, right? Okay, that's what a graph is, right? It's a big set of points. So why?
That has to match the what we looked at before.
In a way, yes, right. Okay, so because remember before for a relation we just had a list of ordered pairs, right?
Yeah.
Okay, so why is a graph kind of the same thing? Why is it also kind of a list of ordered pairs?
Because it has X and Y.
Because what has X and Y though in the graph? Each what? Each point, right? Yeah, each point on the graph, right, has some coordinates, correct? Let's see if we can. I'm not sure if I've drawn this carefully enough, right? Okay, but the points on this graph, right, they have the points on this graph, right, they have coordinates. Like, for instance, this one, what's the coordinates there? 0, 0, right, okay? So that's 0, 0. You have to kind of squint there to read the graph there. That's 0, 0. What about this point right here? That's 2 and 2, right? Okay. What about this point down here?
Wouldn't that be -2?
Yeah, that's -2 and 2. You're right, okay? What about this point here? -2 and what? -2, right? Okay. What about this point up here? -5 and 3, I think. Is that what it is? 1, 2, 3, 4, 5. Yeah, -5 and 3, and so on and so forth there, right? So you can pick off every point on that graph, right? There's a lot of them, okay? But if you had enough time, you could pick off every point on that graph, right? And write down its coordinates. And when you did that, okay, what would you end up with? You would end up with a big set of ordered pairs, correct? Okay? So you see a graph, really nothing more than a big set of, graph is really nothing more than a big set of ordered pairs. So graphs of sets of points, like curves, can also be thought of as relations. Well, so this is a relation. Is that relation a function? Nope. Why not? Yeah, for example, Furman.
-2 has +2, -2 has -2.
Right there, right? Okay. Those 2 points, right? Those two sets of ordered pairs, right? Same input, right? Okay. But different outputs. So not a function, okay? So it's a nice relation, but there's a relation that does not count as a function. Actually, that problem is going to occur a lot, right? Because if you pick any x value here, right? How many different outputs will it have according to this curve? 2, right? One on the top and one on the bottom. So you get lots of inputs with different matching outputs, right? Okay. So A there is a nice relation, but not a function. All right. Well, here's a little bit simpler curve. There's a straight line, okay? So that's an example of a relation. So anytime you have a graph of a set of points, like a curve, that's going to count as a relation. Is that relation a function? Yeah, now here you have to just kind of use a little bit of your intuition, right? Okay? But that is a function, right? So just think about the nature of the curve. If you pick an x value, right, and find the matching y value from the curve, you'll only find one matching y value, correct? Okay? Any x value you pick, right, you're only going to find one and only one matching y value, right? Okay, that's kind of clear from the shape of the curve. That's what's going to happen here, okay? So, yes, B is an example of a function, okay? There's something to keep that we're going to have to keep in mind, right? Lines like this one, except in one really weird case, lines will be functions. Lines are going to be functions. And since we're really interested in functions in this course, that means lines is the type of curve that we're going to be interested in. All right, let's try the next one. So this curve, this curve has all kinds of wiggles in it, so it's not as easy a curve as that straight line is, but does that curve, that set of points, does that count as a function? Montel says no, we have a yes, okay, right? Montel, if you say no, all right, that's a possible answer, but then to back that up with an explanation, right, to back that up with an explanation, you would have to show me what? What would keep it from being a function?
If it would have the same or pairs, but with same inputs but different outputs.
Perfect. Same input with different output. So you would have to show me here the same input with different outputs. So can you pick points off here that have the same input but different outputs? That would keep it from being a function. So can you give me an example of that? No, you cannot. Yeah, okay. And the reason you cannot is because I just don't think it's possible. All right, okay? Yeah, I don't think you can do that. I think each x value here is going to give you one and only one matching y value, okay, for that curve. The visual way of testing this very quickly, right, is just sort of scan across the x-axis very quickly, all right, and then think about where the matching outputs are, right? So here you got a matching output down here, right? For instance, here, matching output there. If I pick out this x value, you got a matching output there. If I pick this x value, you got a matching output down here, right? If I pick this x value, you've got a matching output up there. But do you ever have a case where you have two matching outputs? I don't see it, right? Okay, I don't see that. So I think, sort of by sort of reasoning backwards there, this is going to be a function, all right? Because I cannot find there an x input that has two different matching outputs. Yeah, Uni.
You can also use a vertical line test.
So what do you mean by vertical line test? Okay, so I'm not familiar with that term.
Okay, you check if you have like the same point, like if you draw a straight line at a specific
Draw a straight line, but you're drawing it like this. So what kind of straight line? Vertical line. Oh, so vertical line, right? So you're thinking, I'm going to draw a vertical line, right? Okay, I'm going to draw a vertical line. Can I draw it anywhere? All right, so let me draw a vertical line here, right? Okay, and what are you looking for? Yeah, well, everything on that line will have the same x, right? Okay, so everything on that line has the same x coordinate because it's vertical, right? But if it repeats that point, okay. So yeah, the x values here are all the same, right? So in other words, if that vertical line touched the curve here, but also what? Oh, also below? Okay. Mm-hmm. Oh, if there are 2 points on that line, I see. Okay, all right. But so now it's making it clear to me. So if I draw a vertical line and I end up touching the curve twice, yeah, then what does that tell you? Not a function. Why do you know that that would not be a function? So let's try this as an example then, okay? All right, so what happens with this circle when you draw somewhere a vertical line? Let me draw a vertical line here through that, okay? All right, so that touches the curve twice. So you would say that's not a function, right? But why would that not be a function, according to our definition? So on this vertical line, if we pick whatever this x value is, right, what do we know? So that could be, I don't know if that's 1 or 2 or whatever, but whatever this x value is, because you touch the curve twice, that means what? Because it's not a function because what? There's two different outputs, right? There are two different matching outputs, correct, okay? That's exactly right, okay? So here, see, we were able to draw this vertical line that sliced through the curve twice, right? Okay? And so that tells me not going to be a function, right? Because this input, whatever that input is, I don't know what that x value is, but it's not really important. It's going to have two different matching outputs. So that one cannot be a function. But that will never occur on this curve, right? No matter where you put the vertical line, and you can visualize this pretty easily, right? No matter where you put the vertical line, it's not going to slice through the curve more than one time, okay? So not a, I'm sorry, this one is a function, right? But this one is not a function. But it still always comes back to the same basic definition, because you have more than one output matching the same input here. That is what keeps it from being a function. All right. Okay. So all right. So y'all got those right. This one is a function, even though it's got lots of wiggles in it, right? That one is a function, but the curve here, a circle here, I mean, is not going to be a function. So this is a perfectly nice relation, but not going to be a function. By the way, notice this wiggly line crosses the crosses the x-axis lots of times, right? Many times. So that means you've got the same output occurring over and over again. This output, this y value would be 0 wherever the curve touches the x-axis. Those points, the y coordinate is 0. But that doesn't keep it from being a function, okay? You can have the same output occurring lots of times, all right? It's just that you don't want the same input occurring with different outputs, all right? Okay, so the last one, not a function. But remember that explanation, because I'm going to ask that on a test, okay? Right? And you almost always have the same explanation. It is a function because each input matches only one output. It's not a function because there is an input somewhere with more than one matching output. All right? So here is another way that we like to represent functions by graphs of sets of points, okay? Curves, in other words. So that's our second major way of expressing functions. But we have a third way too, which I'll get to here in a second. But I want to slightly amend my definition of a function, okay? So this definition is equivalent, okay? But it's a little bit easier, I think, in practice to maybe to use, okay? So our formal definition of a function is, it's a set of ordered pairs. Each input matches only one output, okay? All right. But here's a more practical definition of a function. All right, so anytime you have a rule, okay, some sort of rule, or it could be a method, or it could be a system, all right, something that's equivalent to a rule, all right, that you can use to predict or determine an unknown quantity, okay, an unknown quantity, a quantity that you don't know the value of, but you would like to know the value of for some reason, okay. But you can predict or determine that unknown quantity based on a quantity that you do know or that is easy for you to measure. All right? So let me repeat that, okay? So a function is a method that we can use to take a quantity that we know or easy for us to measure, right? Something that's easy for us to measure, and then we can use that rule, that method, that function rule to predict or determine an unknown quantity that's difficult for us to measure for some reason, okay? Or is unknown to us for some reason, all right? That is a function. And in practice, that's really how we use functions, okay? They're kind of systems that we use to take something that we know or that we can find out easily and predict or determine something that we don't know or that's difficult to find out, okay? Right? Okay? That's how functions are practically useful to us, okay? To take something that's known and figure out something that we don't know, right? That we want to know for some reason, okay? That's in practice why functions are useful to us, okay? But now, here's the key thing, right? When we make our prediction, right? When we take our known quantity, right, or the quantity that we can measure, and we use that to make a prediction about the value of an unknown quantity, we don't want to come up with lots of different predictions, okay, right? All right? I don't want someone predicting one value and another person predicting another value. I want us to all agree on what our predicted unknown value is, right? That's why we're so interested in functions, right? We don't want to take the same input and then come up with multiple possible answers for the unknown quantity, see? We'd like to get one and only one answer for the unknown quantity, okay? We want a concrete prediction about what the value of the unknown quantity is. So that's why we're interested in functions, right? Because we have, in a function, you take single input, right? Think of that as the known quantity, and that will give you a single output, right? That's the value of the unknown quantity. It won't give you a range of possibilities, okay? It will give you a definitive prediction, okay? That's in practice the way functions usually operate. Now, I'm going to start off with a very simple example, but we're not going to get into it very far. But just want to explain how a function comes out in this situation, okay? It's so simple that you're going to think it's almost difficult. It makes it hard because it's so easy, all right? Look, but this is often the way functions occur. All right, so suppose you go to the grocery store, right, and you are going to buy some oranges, okay, right? And so you go to the produce aisle, right, and the sign says, okay, today the oranges are $1.20 per pound, all right? The oranges are $1.20 per pound, right? So you take some, you take the little plastic bag and you put some oranges in the plastic bag, right? Okay, and then you go to the checkout counter, okay? And then at that point, all right, you have to determine something. You and the checker have to come to an agreement, okay, about what, so you can get out of the store. So you're purchasing these oranges, right? So you and the checker have to come to an agreement about what quantity. The price, that's right, of course, right, okay? You and the checker have to come to an agreement about the price, all right? What is the price I'm going to pay for these oranges, okay? How do you and the checker determine that unknown price, okay? By using a scale, right? Because what do you do with the scale?
You check the pounds.
Yeah, what do you measure with the scale? The pounds, right, okay. So you see what you're doing here is you are taking a quantity that is easy for you to determine. That's the weight of the oranges, right, okay. The weight of the oranges. That's easy for you to determine because you just put the oranges on the scale, right. So you have a device that will tell you the weight of the oranges, okay. And then you convert that weight into what? Yeah, into a price. That's right, okay? So you take that known quantity, all right? You take that known quantity, correct, the weight, because you both are going to know what that is, right? And then you take that weight and you convert that into the quantity that you need to know, right, which is the price, because that's the only way you're going to get it out of the store, right? You have to know what amount to pay, right, for the oranges. Now, what is that function rule, right? So what is the rule that you use to take the weight and convert it to the price? Let me say cost. Take the weight and convert it to the cost. What's the rule? Each pound is $1.20, right? Okay, so what do you do with the weight?
You multiply it by 120.
Right. It's just that simple, right? Okay. You take the weight, correct, and you multiply that by 120. There is your function rule, right? You take the weight of the oranges, the quantity that you know, right, and you multiply that by the price of the oranges, right, which was $1.20 per pound. Oh, let's write that rule down then. Okay. All right. So the cost, right, or let's say total cost here. The total cost, right, is going to be equal to the number of pounds, right, times what? Times the price per pound, correct, which is, in this case, 120. Now, look, this is very clearly a function, and it has to be a function. Right? In this case, the input quantity, what's the quantity that you know? We just talked about that. What's the quantity is easy for you to measure? The weight, right, okay. So the input quantity here is the weight, right, okay. That's the quantity that you can measure. And, of course, the output quantity here is the cost, right? That's the quantity that you want to know. Now, why is this a function? Because each input, right, each input, each number of pounds, each different number of pounds is going to result in what? That's right, okay. One and only one total cost. Look, the checker is not going to tell you, right, it's either $2.10 or it's $2.50, right? Okay? That's not what the checker says. The checker says the cost is what? They give you an exact amount, right? And they only give you one amount, correct? Okay? So they don't give you two possible costs or three possible costs, right? They give you, and of course it has to work this way, otherwise nothing would ever get sold, right? They give you exactly one amount for the cost, right? So you see each input there will result in just one output. Each number of pounds will result in just one total cost, correct, okay? And that's how we can proceed and pay the right amount and go about our business right, okay? So, see, this rule, right, definitely has to be a function, otherwise not going to get us anywhere, correct, okay? Or it's going to cause all sorts of issues. All right, well, there's a simple example of a function in practice, okay, right, okay? And you use that, or functions like that every day, all the time, right? When you're purchasing stuff. Now, how is this function expressed? We didn't draw a graph here, okay? We did not draw a graph of this function, and we did not have a table for this function. What is this? What would you call that thing? An equation or a formula? Yeah, I would call it a formula, right? Okay? Yeah, so there is another way that we often, frequently, especially in this class, since it's an algebra class, we're going to express functions as formulas, all right? That's another important way that functions are represented in practice. So we've learned three key ways there of representing functions. There are others, by the way, but tables of sets of points, graphs of sets of points, and formulas, okay? Three ways that functions often occur in practice. Okay, let's stop there. We won't have time to work on our homework, all right? So, but you got kind of the big key lessons. Now we're going to go in and fill some details in this lesson next time, all right? So, because we've got to flesh out some of the more mathematical details, but that's the key idea. Key ideas there underlying functions, and we'll be talking about functions every day for the rest of the course. All right, I'm going to stop.